Alright, so this is going to be the first part of lecture chapter 5, weathering soils and sedimentary rocks. Normally in the past, like I said, in the past, what I'm going to use is to be split up into two different lectures. So I'm going to do the same here to try to keep the video length reasonable so that you guys have easier time going through digesting material. Now, a lot of what we're going to be talking about with sedimentation and wet processes, especially weathering, deal with the fact that water is an unusual molecule. Water is something called the universal solvent. Water dissolves more materials than any other known material in the universe does. Part of this has to do with the fact that the water molecule with the shape is called dipolar. If I were to draw out a water molecule, or you basically drawing out a H2O, what we would see is something like this, where we have the oxygen and the hydrogen, and then there's a 120 degree angle of separation between two hydrogens. This causes the molecule to have a positive and a negative side to it, hence the name dipolar. That is what allows water to behave in certain ways. It causes the water molecules to line up. It can cause the adhesion of water to itself, creating a surface tension, or kind of like you can kind of see in my cup of tea, where you can kind of see just right at the edge, the water is kind of growing up outside just a little bit. That molecular adhesion that causes what will line the surface usually called capillary action. In other words, the smaller diameter of the opening higher up water probably may have seen this in different straws in different drinks as you've gotten drinks with straws. So a lot of this has to do with the fact that water is a special material. So what we're going to be talking about now is strictly all external processes. So these are all external processes that are being created in part by the distribution of energy that is coming in from the sun. Some of that has to do with some internal processes in terms of how the surface of the Earth gets shaped, but it's also driven in part by these other external processes. So the first of these is going to be weathering. Weathering is going to be one of two components. You're going to be physical weathering, which means it's going to be the physical breakdown. So you're crumbling things into smaller pieces. Imagine taking a hammer to a brick and smashing it into pieces. That's physical weathering. Or chemical alteration. Chemical alteration is when you have chemical decomposition of a rock. So, if we go back to the example of the basalt that we were talking about last time, where the basalt can have a very dark, black, dark gray color, but over time they will oxidize to red, and that is a part of chemical alteration of the material. Then we have the process of erosion. Erosion is not what most people think it is. Erosion is actually removing the products of weathering away from the location by agents of movement such as wind, water, or ice. And then finally there is mass wasting. Mass wasting is going to have its own separate chapter for us. Mass wasting is the movement of products of weathering down slope under the influence of gravity without needing to have agent of movement like wind, water, or ice. So back to the types of weathering. And again, we have the mechanical weathering or physical weathering, which is the physical breakdown of the rock. There are a handful of different processes that actually cause this. first and foremost among these, I think, is paramount for anybody to understand, is the process of what we call frost wedging. Frost wedging is a freeze-thaw process. So imagine, if you will, you have a crack. Okay? And you fill that crack with a little bit of water. Now you get a little enough that water freezes. What happens? What happens when water freezes? Anybody here ever put a drink in the freezer and forgot about it? Doesn't matter the type. Just probably somebody has. And you've come back and found the plastic bottle of water that is distorted because it's very easy. And the type of drink bottle may have exploded on you, which could have been an ungodly mess inside the freezer. But what happens is the ice forms and it is expanding. The density of ice is actually 90% the density of water, which means that the ice is going to expand. And then when it expands in a crack, it generates a force. And then that force is going to act on the walls of the crack. And when they crack a little bit larger over time. And then if water then thaws, settles deeper in the crack, refreezes, cracks are a little more just like it's a slow wedging process that will take things apart over time. It requires freeze-thaw cycles. It requires several days, if not multiple days of the year, where you're going below the freezing temperature of water, and you have water that's within the crack. Another process is unloading. Unloading is very common for rocks that form at depth. If you have an igneous rock formed at depth, then it forms under pressure. Well, when that rock gets exposed to the surface, the amount of pressure on it is reduced. And so the materials in the outer section of the rock are going to try to expand ever so slightly. They may expand slightly different rates, and that can cause cracking and exfoliations, where they basically get sheeting of material coming off in like layers as the pressure is released. Then we have thermal expansion. Thermal expansion would work greatly in areas like the desert southwest, where we have large potential thermal changes during the course of this time of year. Not uncommon for us to go as much as 40, 50, 60 degrees Fahrenheit swings between high and low temperatures. If you've ever had a ring stuck on your finger, how did you get it off? Well, some people will ice soap or use something to try to pull it off. The easiest way to get it off is to run it under hot water. You run it under hot water, the ring will expand and then you can slip it right off. If you look at barrels are made using the same principle. Rings actually heated up until it expands, slip the barrel, and then it's splashed with a little water to cause the ring to shrink into place and fill the barrel together. Now, different materials will expand and contract at different rates. So if you have material within a rock, different mineral grains that are expanding and contracting at different rates over time, they're going to lose themselves apart. This creates what we call around here decomposed granite. Granite will open up into individual crystals. That's caused mostly by this differential weathering or differential heating effect caused by different minerals expanding and contracting at different rates as they go through the same cycles. Then there's biological activity. This is anything from root wedging, where roots get into the cracks, and if they find the nutrients that they need, they're in the cracks, and they wedge cracks apart. This can be animal activity, a number of different things. It can be all sorts of different things. We're not going to get too deep into it. Then we have the chemical weathering. Now, chemical weathering breaks the rocks into and their components and internal structures of the mineral. When they say that again, I feel like I flipped that back. It breaks the rocks down. It breaks the components down. So it's breaking down the mineral itself. It's changing the chemicals within the mineral, causing them to break down. Again, most importantly, this is going to be water. Without water, it's not going to be as fast. In fact, actually, one of the things that we do know, we'll know later, is that areas that are warm and wet have the greatest amount of chemical weathering around. Areas that are warm, dry, have very little chemical weathering. So some of the major processes from chemical weathering is going to be dissolution. Dissolution is where you have small amounts of acid that are in water. Most water is slightly acidic in the atmosphere because it absorbs carbon dioxide, which forms carbonic acid in the water. It's not something we have to worry about. Generally speaking, we can live in the vat of carbonic acid for years and not have any problems from it. It's such a gas that over time, and again, geology is all about time. It has a significant process it can do. So basically, what it's going to do is that acid is going to attack the soluble ions within the material and leach them out of the mineral. They're going to go into the water supply. Then there's oxidation. Oxidation is where compounds react with oxygen. So hence the salt is oxidizing as the oxygen reacts with the iron that is in the pyroxene or the amphibole or the olivine that's in this, and it pulls the iron out and oxidizes it. Most of the magnesium minerals actually undergo this process. When there's hydrolysis, this is a reaction with water where hydrogen ions attack and replace other positive ions in the structure. And that can actually change things around as well. So basically, what this is going to do is it's going to do basically a couple of things. The decomposition of is going to take what are relatively unstable minerals in the environment and try to make more stable minerals or more stable substances. Generally speaking, you're going to either retain minerals that are stable or generate new minerals that are stable. Sorry about that. So basically, the alterations by chemical weathering are going to decompose unstable minerals. It's going to generate or retain minerals that are stable. And it's going to cause some physical changes, namely the rounding of corners or edges. Now, when we look at the rate of weathering, advanced mechanical or physical weathering really aids chemical weathering. The reason for this is very simple. Chemical weathering requires surface area. It only works on the area that's available to the chemicals. So let's imagine that we have a cube. And let's say, for the sake of argument, that cube is 2 centimeters on a side. Okay? What's the surface area of that cube? Well, it's going to be 2 by 2 by 6 because of the number of sides, which is going to be 4 by 6 or 24 square centimeters. If I cut that cube in half in every direction so that I make 8 cubes, what have I done to the surface area? Well, now each cube is 1 by 1 by 6, which means each cube is 6 square centimeters, but now I have a total of 8 cubes, which 6 times 8 is 48, so I've doubled the surface area. So every time a rock gets broken up mechanically, it increases the surface area that's available for chemical weathering. Okay, the greater the surface area available, the greater the amount of chemical weathering that can occur. Some other important factors. The type of rock material is going to be very important. For example, let's say I have a rock that is made out of a calcite, like a limestone or a marble. That's going to be much more reactive to a weak acid solution than, say, a quartzite, a rock that's made of nothing but quartz. So we can see that the type of material is going to have a bearing based on the type of weathering that's occurring. Basically, when we look at Bowen's reaction series, interestingly enough, Bowen's reaction series not only shows us which minerals will form first to last from a cooling magma body, but it also is inversely the stability of those materials. So whatever is at the top is the least stable, whatever is at the bottom is the most stable from a weathering standpoint. Then there's the climate. Climate and temperature and moisture are very, very crucial. Again, areas that are warm and wet, much more weathering than any other places in the world. Basically, if you can get someplace that's warm, wet, but occasionally goes through freeze thaw, you can really smash rocks apart. And then we get something called differential weathering. Now, differential weathering occurs because rock units do not weather the same. For example, here in the American Southwest, we see slopes and we see cliffs in the mountains. Typically speaking, if we're dealing with only sedimentary rocks, we can pretty much identify what's what by the nature of the topography. Cliffs tend to be limestone, slopes tend to be sandstone, silts, and shales. However, if we go back east, it's the reverse. Sandstone will be cliffs and limestones will be slopes. That has to do with the way the materials are weathering and what's causing the weathering in that area. So it creates many different things. Another way you can get differential weathering is by having a more resistant material on top of a less resistant material. If you think of like Monument Valley, many of the monuments in Monument Valley are actually formed in that way. You have a cap rock of harder basalt that's left on top of many of those features, and then it's the softer material underneath that's been eroded away, except for what's directly under the cap rock. All right, so let's talk about soil. What is soil? Soil is a combination of mineral material, organic matter, water, and air that is the upper portion of what we call the regolith, or broken up rock material, at the surface of the earth that supports plant life. So that's really a very key component. It has to support plant life, which means it's going to have organics in it. And we're going to look at the formation of soils. Now, generally speaking, there are 5 key controls on soil formation. First and foremost is, what is the nature of the parent material? Obviously speaking, you're not going to get a soil that is going to be different from the parent material that you created from. Now, in this, that means we can have 2 different types of parent material, or 2 different types of soils. There's residual soil, which is the parent material is the bedrock that's underneath the soil. This would be very much like if you're on top of the hills around us, especially where the Nogales Formation is exposed down here in the Nogales-Rio Rico area. The material is usually going to be made from that material, unless you're in the older alluvial deposits. Then you're in what's called a transported soil, because the soil is something that was brought in, especially down by the river. You have the floodplain deposits. The material that are making up the floodplains is different than the bedrock. So that's a transported soil. Like every geological process, time is a big necessity. It takes time to develop a mature soil. If you look at our soils in Arizona, they tend to be very immature. In part, there hasn't been enough time, given the rate that processes happen in our environment, for soils to properly develop. And that gets to climate, which is the most influential control over soil that there is. The temperature and precipitation elements of the climate, the local climate, exert the strongest impact on the soil formation. So there are soils that are specifically developed for desert environments, for Arctic environments, for tundra environments. So we see this in the way we are able to identify soils. Plants and animals are also very crucial because they are going to influence the amount of organics, right, and the type of organics that are going to be incorporated into the soil over time. And then finally, there's slope. Steep slopes tend to have very poor soil formation. Optimum terrain is a flat, slightly undulating terrain. That gets the best soil formation. But you can see also that slope orientation can matter. Just looking out here, if you drive between Nogales and Tucson, you can note that there are some hillsides where a slope facing north has different vegetation on it than the slope facing south. And this is in part due to the fact that the soil formation is different on those two slopes, even though it's on the same bedrock itself. So let's talk about the soil profile. This is if we were to cut through the soil. Now, what we're going to draw out and talk about is going to be the ideal soil formation. Not necessarily what we have here, but this is what's going to be the ideal situation. So we're going to start with the idea of a column like this. Now, at the bottom of the column, I'm just going to put it down here with a jagged line. We're going to have bedrock. Okay? And above that, we're going to have our unaltered bedrock. We're going to call the regolith. That's just going to be the bedrock that's broken up. Okay? So the rest of this is going to be what we call the soil, our soil column. Now, at the very top is going to be the O layer, the O horizon. O for organic, or sometimes referred to as the humus, H-U-M-U-S. This is the organic material that is making up the soil, the organics in the soil. The O horizon is nothing but organics. Below the O horizon is going to be the A horizon. Okay? The A horizon is going to be the area where you have organic and mineral matter mixed together. This is where you have most of your biological activity is occurring. So this is where you're going to find your plant roots, your animal digging through it, the critters that are living in the soil and whatnot. If we take them together, the O and the A horizon are what we call the top soil. Okay? Now, out here in the desert Southwest, this is very, very thin. Under some trees, under some mesquite trees, it's maybe an inch thick at best. In the rough desert environment, it's almost non-existent. Now, below this level is going to be the E horizon. Okay? This is what we call the zone of eluviation. If I pronounce that right, yeah, eluviation or leaching. Basically what's happening is as water percolates down through the topsoil into this horizon, it's going to wash stuff out of the material. So it's washing things out. Soluble materials, fine particles are all getting washed out of that. That's going down to the B horizon, or the zone of accumulation. Sometimes in areas you'll see this as a thick layer of clay. Altogether, the O, A, E, and B are going to be the solume, or true soil. Okay, so this is the true soil area. This is when we study soils and classify soils, we're looking at this entire thickness of soil. Now, we're not going to get into the classification of soils in too much detail here, just simply because it gets very complex very quickly. I do want to say that it's based on a taxonomical type of hierarchy. So very much like the way that we set up the classifications for life forms, if you were to study paleontology or biology. We emphasize the physical and chemical properties within the soil profile. Basically, there are 6 hierarchical categories that run from order, which is the broadest category, down to series, which is the most specific. Most of the names are derived from Latin or Greek, and we basically have 12 general orders that are recognized. Beyond that, I'm not going to really get into it for you guys. The arid soils are the most common one for us here in the American Southwest because they're based on arid environments. So you might want to know what an arid soil is. Beyond that, there's soil erosion to finish this out. Soil erosion is in part a natural process. It's the recycling of the materials within the earth itself. The rate of soil erosion is going to be determined on the characteristics of the soil, the climate that it's in, the slope of the land, the cover of vegetation. All those play a role. Many regions, the rate of soil erosion, unfortunately, have been greatly increased because of human activity, to the point where soil erosion is actually faster than soil formation. This can lead to problems like desertification and other issues like that. In part, this is because, unfortunately, many times humanity seems to have to learn lessons the hard way over and over instead of learning from other past mistakes. We now try very hard to undergo processes to try to alleviate that. For example, we learned a lot of lessons during the Dust Bowl of the American past, where areas lost as much as 30 meters of the topsoil gone with the wind. And that was due to a combination of the plowing of the Great Plains with the steel plow, which pulverized the already fine-grained soil into literally powder, followed up with a drought conditions that just blew the soil away once the vegetation was gone. Today we now try to do a lot of large-scale cultivation on what they call on the contour, so that they plow on the contour, so that they create a system where water is captured on the hillsides and soaks in instead of just running off, which can actually increase and worsen soil erosion. So with that, that's going to cover the part about weathering, and I'll do another one on the actual products of the weathering that we create, the sediments and then the rocks from them. I'll talk to you guys later.